All right, so we just talked about the X-ray tube, including the anode and cathode. Now we're going to talk about mainly what happens at the anode, which makes X-rays. So remember, kinetic energy only belongs to things in motion. So once something is in motion, it has a kinetic energy equal to 1/2 the mass times velocity squared. Just a real simple formula. We won't actually apply that, but that's a formula that you may want it to remember. 1/2 mv squared. So the X-ray system is pretty amazing. It moves electrons from cathode to anode at a very precise kinetic energy according to what we've set on that operating console. Now, while most of this action results in heat, so about 99% is heat, we still get just enough of it, that just 1%, results in enough X-rays for us to get a diagnostic image. And it's kind of showing you here, we have these projectile electrons from the cathode traveling through that vacuum. So all they're going to do is interact with the atoms of the tungsten target over here. But you can see what mostly happens is excitation of these target atoms here. And excitation is just heat. But we can also get characteristic radiation. So here again we have our tungsten atom. It's kind of what it looks like here. And remember, in that K-shell, we have an approximate binding energy of 69 kiloelectron volts of energy. So that's how much energy these electrons here in the K-shell are being held to the nucleus with. So if an electron from the cathode interacts with an inner shell electron of this tungsten atom, we could get a characteristic X-ray. Now this is because an outer shell electron will actually release its energy in the form of an X-ray as it drops down to fill the inner shell void. So remember, we are actually ionizing this tungsten atom, right? So our filament electron comes in and it gets rid of one of the tungsten's electrons. It pushes it out. Now, what I do want to say though is that neither this K-shell electron nor that projectile electron, which was deflected and pushed away, so these electrons here that are kind of flying off due to that interaction, neither of those are going to be the X-ray, okay? The X-rays come from when the outer shell electrons here drop in to fill vacancies, the vacancy left by this K-shell interaction here. They release energy, electromagnetic energy in the form of X-rays to help this atom regain stability. Now, only K characteristic X-rays are useful because they have the most energy to give to produce X-rays. So the farther out we get, the less useful those X-rays are because they're so weak, they're likely to just get stopped by filtration in the tube, or if they do get through, they're just going to stop in the body, most likely, if they even make it to the body. So further on characteristic radiation, again, the electron ejected from the tungsten atom is not the X-ray. It's just going to fly off and fill a void in another atom. It's going to help regain stability to all the other tungsten atoms, which are all trying to, again, become regular tungsten atoms again and have their preferred number of electrons. The cathode or projectile electron also does not disappear, and it's not the X-ray either. It's going to be deflected and either be conducted through that anode or fill another vacancy in a tungsten atom. But remember, any excess electrons we have are conducted by the anode back into the system, and nothing is created or destroyed. It's only reused and put in another spot. The X-ray itself comes from that electromagnetic energy emitted when those other electrons drop down and fill the voids left.